Welcome back to multivariate calculus. In this video, we're going to discuss the angle between two vectors. Once again, this is going to be an idea that you should be familiar with when it comes to vectors in the plane already. Extending it into 3 dimensions is a little bit interesting. I also really like this because it's one of the first places in this course where I can point out that the definition that you're used to is really backwards of what we are really doing. So we're going to start by looking at the vector dot product, sometimes called the scalar product of two vectors, just to make things confusing, which is completely unrelated to the scalar multiple and completely unrelated to the vector product that we'll be talking about in a later video. So calling it the dot product is the easiest way. But you have probably learned in the past that the dot product is defined based on the cosine of the angle between the vectors. In serious geometry, in the axiomatic definition of geometry, it actually goes the other way. We define the measure of an angle based on the dot product and based on a formula from that. So this is going to define how to measure the angle between two vectors in space. So without further ado, let me get my head out of the way and let me remind you of the dot product. For vector u, which is going to be ux I hat plus uy j hat plus uz k hat, and vector v, which we're going to write as vx I hat plus vy j hat plus vz k hat, we define u dot v as ux vx plus uy vy plus uz v z. The important thing to remember about the dot product is that when you take the dot product of two vectors, the result is a scalar. All right, so this is a scalar value, not a vector value that we get as a result. So for example, if I have the vector, and I'm writing this one in component form instead of in unit vector form, just to remind you that that's still a thing we can do. I have the vector 2, 5, or 2, negative 5, 3, and I have the vector 3, 2, negative 5, and I want to dot these together. I multiply the x components. No, I don't have to write this line out. No, I don't expect you to ever write this line out, but let's make sure that it makes sense where these are coming from. X components, 2 times 3. Y components, negative 5 times 2. Z components, 3 times negative 5. And when I'm trying to do these by hand, that's usually the second line that I write down. And then I can figure out from there, 6 minus 10 is negative 4. Negative 4 minus 15 is negative 19. All right. And that takes us to the idea of the angle between two vectors. Given two vectors u and v, we are going to define the angle as u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta, where theta is the smallest angle between them. In 3 dimensions, the smallest angle between them is a fairly loaded concept. There's a lot going on there. So first of all, as we're going to establish in more detail a little bit later in this course, if you have 2 vectors, any 2 vectors, that will uniquely define a plane. So when we have 2 vectors like this, we are looking at a plane in some orientation. It's probably not going to be the x, y, yz, or zx plane. It's probably going to be a plane on some random angle, but there is exactly one plane which contains both vectors. And so we are looking at the angle in that plane. And of course, whenever you have 2 vectors, there's always a short way and a long way. So we're going to look in the plane. We're going to find vector u. We're going to find vector v, which might be in this orientation or might be the other way. But there's a short angle between them that we'll call theta. And there's a long angle between them, which is going to be 2 pi minus theta. Whichever order, whichever one is u, whichever one is v, that doesn't really matter. What matters is the smaller and larger of the 2 angles. All right, so we just looked at a couple of vectors. Let me get my head back out of the way. Let's scroll up a little bit. Let's take a look at these 2 vectors. I guess I have to name which one is which. So let's let u be the vector 2, -5, 3, and let's let v be the vector 3, 2, -5. And we know that u dot v is -19. So in order to figure out the angle between these vectors, we also will need the magnitude of u, which is going to be the square root of 2 squared plus 5 squared plus 3 squared. 2 squared is 4, 5 squared is 25, 3 squared is 9. 4 plus 25 is 29, plus 9 is 38. And the magnitude of v is going to be the square root of 3 squared plus 2 squared plus 5 squared, which is also 38. And while 38 is a really hideously ugly number, the square root of 38 times the square root of 38 is just 38. So u dot v is -19. And then we have root 38 times root 38 times the cosine of our angle. Root 38 times root 38 is 38. And very conveniently here, 19 divided by 38 is 1/2. All right, so now all we need to do is remember the angle whose cosine is -1/2. Right? I know this is going to be a second quadrant angle because cosine is positive in the first and third quadrant and negative in the second and fourth quadrant. But we don't want third or fourth quadrant because that would be the longer of the 2 angles instead of the shorter of the 2. And I know that the cosine of pi over 3 is 1/2, which means that the remainder of this angle would be 2 pi over 3. And so we have found the angle between those 2 vectors. It's 2 pi over 3, or 120 degrees if you are the type who really prefers degrees. In calculus, degrees are evil. That doesn't change. All right, so we can find the components of an angle. That's kind of exciting. I'm sorry, we can find the angle between two vectors. That's kind of exciting, but finding angles in and of itself is not all that useful to what we want to be doing this semester in calculus. Instead, I'm going to follow that up with two other applications. The first one is to break a vector into components. So if we have two vectors, vector u and vector v like this, one of the things that I can do, given any two vectors, is break another vector into components. So I can look at vector v as being a path along vector u and then a path perpendicular to vector u. We call this the projection onto u of v, and then the other part we don't really care to give a name to, but we can break that up into components. And figuring out how to break that up into components is pretty easy now that we have an angle named here. Because the projection onto u of v divided by the magnitude of v itself. So the magnitude of the projection onto u of v divided by the magnitude of v should be the cosine of the angle between them. I forgot to get my head out of the way. There, now you can actually see the formula. And we just established that the cosine of the angle between them is the magnitude of u times the magnitude of v. I'm sorry, right? The dot product u dot v is magnitude of u times magnitude of v times the cosine of theta. So solving for cosine of theta, you get u dot v divided by magnitude of u times magnitude of v. All right. Very conveniently, there's a magnitude of v in the denominator of both of these. That's going to go away. So the magnitude of the projection of onto u of vector v is the dot product u dot v divided by the magnitude of u. And since it's pointing in the direction of vector u, then we can get the direction of this by simply multiplying by a unit vector in the direction of u. And a unit vector in the direction of u is vector u divided by the magnitude of vector u. In order to make this process a little bit easier to manage, very often our first step is going to be take vector u and find a unit vector, which means that magnitude of u is going to be 1, and that makes this calculation really easy by comparison. Let's find the component of vector v. How about 2i plus 3j plus 4k in the direction of the unit vector u hat is going to be 6/7 I minus 3/7 j minus 2/7 k. And so, uh, again, we have a unit vector that we are looking at, which really makes the calculation here easier because these magnitudes are going to be 1. But don't just take my word for it. You should look at that vector and make sure that it is in fact a unit vector. Since it is, that's going to make our life really easy. We're going to simply take the dot product of u dot v and multiply it times vector u. That's all that this problem is asking us to do. So we take that dot product. 2 times 6/7 is 12/7. 3 times -3/7 is -9/7. 4 times -2/7 is -8/7. We'll multiply that times 6/7 I minus 3/7 j minus 2/7 k. 12 minus 9 is 3. 3 minus 8 is -5. And then simply distribute. -5/7 times 6/7 is -30/49. -5/7 times -3/7 is going to be +15/49. And then 10/49 in the k direction. Right. One more tool that we can look at when it comes to trying to work with the dot product is that knowing the angle between two vectors gives us some idea or some easy way of measuring when vectors are parallel or perpendicular. If the angle between the vectors is 0 or pi, 180 degrees, then the vectors are parallel. If the angle between the vectors is pi/2, 90 degrees, then the vectors are perpendicular. I can turn that into a pretty straightforward theorem. Well, the cosine of 0 is 1, so u and v are parallel if and only if u dot v is actually equal to the magnitude of u times the magnitude of v. And cosine of pi is -1, so I guess this will be a plus or minus going on here. U and v are perpendicular if and only if u dot v, well, the cosine of pi/2 is 0, and anything times 0 is still 0. So the two vectors are perpendicular if and only if their dot product is 0. Huh. So there's something for us to bite our teeth into. If I have vector u, 2i minus 2j plus k, and I have vector v, 3i plus 2j minus 2k, then I can ask the question, are these two vectors parallel, perpendicular, or neither? And in order to answer that question, I'm going to first look for the dot product between them. If I dot u dot v, it's going to be 2 times 3, which is 6, minus 2 times minus 2 is minus 4, 1 times minus 2 is minus 2, 6 minus 4 minus 2 is 0. That's the easiest case. If the dot product is 0, then the vectors are perpendicular, no further questions to ask. If the dot product is anything else, then we have to figure out the magnitude so that we can actually calculate the angle. Helps if I write down the right problem. Similar problem for you to try on your own. This time the vector u, 4, negative 2, 6, and the vector v, negative 6, 3, negative 9. And we again are asking the question, are these two vectors parallel, perpendicular, or neither? So take a few minutes, see what you can do with that problem, and I'll see you in the next video.